right. Can you guys see the screen okay that I'm sharing?
I can see.
You can?
Yes.
Okay, good. So my name is Nick Allgood. I'm going to be talking to you about some quantum algorithms today. I know you guys have covered them as part of your class, but I know you guys have been focusing a lot about quantum annealing. This is going to be more gate model type of stuff, and it's kind of the other side of it, if you will. And I'm trying to figure out how to use my. Okay, so who am I? I'm a PhD student here at UMBC. I'm in computer science. I actually, I'm hoping to get candidacy in early 2021. My thesis defense is actually Tuesday, the 28th at, I believe, 11 a.m. During the day job, I work as a consultant. I primarily do network architecture of classical networks, but I do a lot of other things too, including a lot of software development and automation. As my research interests are definitely quantum computing, and I really am getting into the quantum teleportation and the communication, some cryptography, not as much yet, and then some just general cybersecurity. And in particular, malware analysis and research has been an interest of mine, and that's actually what my thesis will revolve around, and we'll get into that a little bit. And then, classical communication networks and cybersecurity. Okay, so we have, I'm going to go over a brief review of quantum computing. There's not going to be, since you guys have been doing some of this, I'm going to go over it somewhat fast, but I'll go, if there's any questions, obviously feel free to ask. Then I'm going to go into three of some foundational quantum algorithms that are gate model based. The first being Deutsch-Jozsa, the second being Simon's algorithm, which is actually an algorithm for something known as Simon's problem. And then I'm actually going to tie that into some of current research I'm working on with Dr. Lamonaco and Ajinkya Borle here. And then I'm going to go into Grover's algorithm, which also ties into some current research I'm working on, but that's more of my master's thesis. And then part 5 will be time for you guys to ask questions. Let's see if I can do it. Okay, so part 1. So I know you guys have been dealing a lot with quantum annealing, so I don't really have to explain too much about that. But adiabatic or quantum annealers used to find the global state. They want to find a global minimum or a global maximum based on Ising Hamiltonians. Pretty basic stuff there. Then we want to get into analog, which is actually are also known as quantum simulators. And we're trying to simulate complex quantum interactions and being able to detect untraceable quantum details. And over time, quantum simulators are actually improving dramatically. It's kind of a weird paradox to think why are we simulating this, and then we have the real hardware. But over time, the algorithms for the simulators, and there's a whole other dimension when it comes to, I forget the exact acronym, but it's essentially like I don't know if we call it quantum assisted, but it's like partial quantum, where part of it's quantum, part of it's classic. And then that kind of goes into what hybrid quantum computing is, which I'll talk to in a second. A universal quantum machine is essentially it's the holy grail, so to speak. And what I mean by that is it's the most general purpose quantum computer that you could have. So you could essentially do anything on it, much like a desktop version of it, essentially, more or less, is a very simple way to put it. And then hybrid quantum computing, I think D-Wave has a machine like this, and I don't know too much about the intricacies, but from what I've read, it's essentially just quantum computer and a classical machine shoved into one, and any of the post-processing or anything that's classically done needs to be handed off to a classical CPU, probably through some internal traces and buses. And then it uses the quantum CPU for other things. Then there's measurement-based, which I don't know a lot about this one either, but you start with a fixed entangled state, and then you just keep taking measurements over and over until you get your desired results. And then a little bit about qubits here, just to kind of go over it. It's a quantum bit, or the quantum equivalent of a classical Shannon bit, which goes way back to Shannon and information theory, who kind of was a founding father, so to speak, of digital circuitry. And it's 1 or 0, true or false. A qubit can be 0, 1 at the same time, or 0 or 1, with one number being the probability of 0, and then 1 tells you the probability of being 1. And so one thing I wanted to point out here is we like 0 and 1. Quantum physicists and mathematicians like to start with 1. And there's actually a quantum mechanical reason for it, but usually you'll see some stuff in literature being referenced as -1 and 1. And I think some of the quantum annealing stuff kind of has that same reference too when it comes to the energies, but I might be a little off there. So how they're represented, we have bras versus kets, just a vector space as a column. We have a bra, which is as a row, and it may seem like they're the same, and in some cases they can be. However, when you take them separately, they can actually have different uses and different meanings. So that's why they usually represent them separately. And if I'm going too fast for this stuff, let me know. I'm just kind of going fast because I know you guys have probably covered some of this. And kets and bras, we represent a single qubit through it, and it's usually you see it represented as kets. Sometimes you'll see it as, it really depends on what operations they're trying to do, is how you'll see that. And a single qubit is really nothing but a vector space, and more specifically, I can't think of the one now. A Hilbert space. Thank you. I couldn't even think of that. A Hilbert space. So, and we're essentially do some math on them. You know, I'm putting this very lightly here. And if we want to expand our quantum system, when we have 2 qubits together, we do a tensor, or more formally a Kronecker product on the 2 qubits, and we get a larger vector space. And that exponentially increases the size of our quantum system. And one other thing I wanted to point out that was, and it depends on which literature you read. Sometimes this is the actual tensor symbol in the math piece. However, in some of the, especially some of the physics heavy literature, you'll see them represented like at the bottom here, where the ket and the bra are kind of facing each other. That implies this tensor operation. So, and these qubits together make quantum registers, and similar to classical registers, they are where we push and pull and stuff multiple pieces of data in and out, do calculations, manipulating them, so to speak. And so essentially everything is a vector space, so multiple qubits together make a quantum register. The quantum register is the resulting size vector. And then we have quantum logic gates, which are very similar. This is kind of where it's going to start to differ a little bit from quantum annealing, is that we actually have quantum logic gates, and it's similar to classical logic gates, where you have inputs and you have a gate that represents some operation, then you have an output. And they're actually the foundational pieces of a universal quantum computer. And they're represented as a unitary matrix, which, if you're not sure, is a special type of square matrix. And then many of the gates that you'll see are single qubit gates, but there's a lot of them that also operate on at least more than 1 qubit. And when a gate operates on more than 1 qubit, this actually causes quantum entanglement. So here's some common gates here that you've probably seen, but I'm going to go over them kind of quickly. You have your standard poly gates. X essentially is the equivalent of like a NOT gate. It negates or knots, does a knot operation. You have your Y gate, which is you rotate along the Y axis, and then you have your Z gate, which does a phase flip or rotates along the Z axis. And it'll kind of become clear. I have some information about some geometric representation that'll actually I think it'll make a lot more sense in the coming slides. And then you have your Hadamard gate, which puts things into superposition. And then a couple of examples of some multi-qubit gates are the swap gate, which swaps the value of 2 gates, and then the C knot, which is considered a control knot. So on one qubit you have what's known as the target, then on the other you have the control. And I think I go into that a little bit further on. If not, I can try to bring it up. So these are used to form quantum circuits, which is just a bunch of gates across qubits. And so, for example, we have our Hadamard here, and then here is a really good example on the far left. There's like a black dot, and then it goes down to a target symbol. What this black dot is, this is actually the piece of it called control, and then the actual target down there is the target. So what this means is if the value is 1 here, then that's actually going to trigger that to actually put the NOT operation on the second qubit here. Now, if this is 0 and nothing happens, it just passes through no problem. So, and then we can see here, if this gets set to 1, this is 1, this will trigger this to trigger this other qubit. That's just a really simple example. Then here's an actual circuit. I don't know what this is, but this kind of talks about, we have our single qubit gates and then we have our multi-qubit gates. So, well, single qubit, the 2 qubit gates where we're affecting. So a little bit more about quantum systems and the quantum states. Formally, a quantum system is a portion of the whole universe taken to analyze the wave-particle duality within that system. A quantum state is essentially a snapshot of that system at the present time. So all the data, all the linear combinations being performed at that very moment it's measured is actually what your state is and becomes. Now, obviously the state can change after the fact, and that's very common, but that's kind of whenever, you'll hear this actually called collapse in some literature, and there's kind of an argument if that's the proper word for it or not, where, you know, you don't look at it, you don't observe it with any equipment, it's fine, it does its thing, and then you measure it, and then it just collapses into this one piece of data, so to speak. And then I know you guys with quantum annealing, you guys are dealing a lot with the energy and the amplitude as well. And this is all the quantum mechanics stuff coming through, because this is really just a very thin layer on top of quantum mechanics. It's definitely getting its own. There's a lot of research going on to it, but it's getting there. But still, we're still at a really, really low level. And I actually heard someone talk at the university, I think in summer, and there's still a lot of ditches being dug and need to be dug. So that's kind of where we're kind of like back in the 1950s of classical computing, where we're figuring all this stuff out and we're making all these paths. And so we're really at the bare metal here. And then quantum measurement is actually how we actually measure it, but it's typically represented as a matrix called an observable. So we have an observable crafted to a specific state that we want to measure, and then we apply, you know, in the mathematical piece, we apply the matrix to that, and then we get hopefully what we're looking for within a certain probability. So, and then a little bit about quantum entanglement. This is where, formally, it's where a particle interacts with another particle, and you can't tell their quantum states apart. In quantum computing, this, as I mentioned, you have a multi-qubit gate applied at least 2 qubits. Once applied, you can't actually, you have a qubit at each side. You entangle them together. You can no longer really determine what belongs to what qubit. It's its own. It's like a brand new entity. And a CNOT is one example that you saw earlier of that. The swap is also, and there's several others too. And then I want to talk a little bit about, I don't know if you guys have covered a little bit about noise, but noise in quantum systems is really important. And there's 2 different types. There's quantum noise and there's classical noise. Classical noise, that's usually due to more your physical factors, such as vibrations, variations in the thermal energy and the laser emitters. It could be about anything physical. It could be just unknown reasons. Quantum noise is actually more formally known as decoherence. And what this does is this basically means we have a loss of quantum behavior over time. So, and quantum physicists really love studying noise, but as computer scientists, we want to get the most accurate result possible, and noise causes inaccurate results. So that's, and actually the more gates you have, the more noise you introduce. So that's part of a research area as well, is trying to get algorithms running on as few gates as possible to get in decompositions and so forth. Now noise is interesting to computer scientists because there's a whole field with quantum error correction that you can actually use to, okay, you know there's going to be noise. What's a good way to do that? And I know Dr. Dorban has, I think it's called MQC. He actually had, and I haven't looked too much into that myself, but I've heard pretty good things about that being a very good algorithm for reducing noise. But that's where an interest is there as well. And then, so with some of those groundworks out of the way, I'm going to get into a little bit of Deutsch-Jozsa. Deutsch-Jozsa is a relatively simple quantum algorithm, but it's very foundational, and it's one of those things that it's so simple that it can be confusing, and it is. And the joke is, if you think you understand quantum computing, you're wrong. You're lying to yourself. And I hear that said by many people in the research area. And it's inspired many other algorithms, such as Simon's algorithm, Grover's algorithm, Shor's algorithm, many of them. They didn't necessarily come from this, but this inspired, hey, I got an idea. He's done this, let's do that. And the big concept here is there's this thing called an oracle or black box computing, which I don't think you have on quantum annealers, but essentially it's this entity that it takes these inputs, it gives a certain output, and based on certain expectations, but you don't have a clue how it works. And it's an interesting problem because this whole concept, again, is carried over from quantum physics, and quantum physicists really don't care about the inner workings of a black box. And it's actually usually in their best interest if they avoid it altogether, because they're working on their own problems. But we're computer scientists, so the problem is, well, we have to implement this if we're doing Oracle-based computing, so we actually have to care about that. And so if you go looking through some Oracle-based algorithms, you're seeing, okay, well, the literature references some Oracle or some black box, but what does that, and here's what it does, but how does it do it? I have no clue. That's what the literature always says. So you're left to your own devices a lot of the time, which is, it's fun and frustrating at the same time, because they spend all this time thinking and talking about the application and doing that, but how it actually works, that's just kind of clueless. But, and at a very, very high level, you can almost think of it like an API function, where if you're doing an API call and you don't know how any of this stuff works, but you just know, here's my input parameters, here's my outputs, what I expect, but I don't have a clue how they've implemented it. It's kind of similar to that at a very conceptual level, though. I don't want to say it too detailed because I don't want to get myself in trouble there. But Deutsch-Jozsa, more specifically, was created by David Deutsch and Richard Jozsa in 1992. And the formal definition is, we're given a black box quantum oracle that implements some function f that maps 0 to 1 to 0 to 1. The function takes an n-digit binary value as the input and produces either 0 or 1 for each value. So, and the idea here is that we're trying to determine if the given function, if it returns a 0, we have a constant function. If it's return a 1, then the function is actually considered balanced, where half the inputs will return 1 and half will return 0. And that's all it's doing, is determining, is this function balanced or not. And then this is actually some code that I've actually modified a little bit with Python and IBM. The IBM Q machines use something called Qiskit, which is a Python API. You can install it through pip. Pretty standard stuff. It's all pretty well organized. And they change the API a lot, so that's something you have to kind of watch out for if you're doing some stuff, because sometimes it may not work. It may break some other things, but it's pretty experimental stuff. But it's coming along pretty well. So it's pretty standard Python stuff. So I know D-Wave uses the Python API too, and there's differences, but it's not too astounding. So, you know, you're using NumPy and some of the other scientific libraries. You get your random here. You have your constant oracle set up. You set up a balanced oracle by creating a quantum circuit. You go through, say this is your string that you have, and you basically determine if there's a 1, this qubit, it's balanced. And then there's this thing called a barrier they use, and this is only used for visualizations and representation. And so essentially what it does, and I can actually kind of point it out when we get to some more quantum circuits, is it's basically a line between operations. So it's like, okay, you have your initialization phase, line, your oracle, line, and so forth. And that's essentially all it's for. It doesn't do anything to the circuit at all. It's pretty much for visualizations. So, and then we kind of continue on through here. Then we eventually make our Deutsch-Jozsa circuit. And we apply a Hadamard, we do an X, then we do a Hadamard, and then we add our balanced oracle to it. And then we apply some more Hadamards to it, and finally we actually measure the circuit. And I think I have some results. Oh, I didn't actually put the results on that one. But essentially what it does is it should return, it just returns 1 or 0 if it's balanced or if it's considered constant. And I didn't get too deep into that one. And then here's the link for it here that actually has, because Qiskit has a free textbook as well. I may have found 1 or 2 errors in it, so just kind of be careful. You may have to play around with some of the things to get it to work in the way they say. So now I want to get into a little bit more into Simon's problem. Now, Deutsch-Jozsa is pretty simple, but Simon's problem is a little bit more complex and a little bit more detailed. And this is actually where one of my papers comes in. I'm hopefully getting published soon. So a formal definition is, for a given function using a black box or oracle, we have some function of x that takes 0, 1 to the n, maps to 0, 1 to the n, and we have to we promise to satisfy a property for some s inside of 0 to 1 to the n for all x and y within 0 to 1 to the n. The function of x equals the function of y if and only if x mod 2 y is within 0 to the n and s. In the case of s is 0, our function is actually a 1-to-1 function. Any other s value is actually a 2-to-1 function. And that's kind of where it gets more interesting. If it's 1-to-1, it pretty much maps 0 to 0. So, and we can actually go further on the formal definition as f is the function such that f of x equals f of x mod 2y for all x within 0 to 1 to the n, and given a fixed unknown s within 0 to 1 to the n. And that's the very formal mathematical definition, but I have a little bit simpler of a layperson definition because I like simple things because they don't make my head hurt as bad. So we have a black box in Oracle that takes x and y, and we produce x and then f of x mod 2y for an input bit string for a hidden bit string, and we map it to 2 outputs. And we're trying to find we're trying to find this hidden bit string known as s, but sometimes you'll see it called a or a period string in some of the literature. It really just depends when it's written and who wrote it. And what it actually returns is Simon's algorithm will return a series of linear equations that can then be solved classically to find the hidden period string. So it may not seem necessarily like it's that useful, and it may even seem more of a proof of concept, and it really kind of is. However, there are some uses for this. One is a little bit about my research, which I'm going to talk about shortly, is work with Dr. Lamonaco and Ajinkya Aberle about using Simon's algorithm to determine the overall quantumness, if you will, of a computer, and specifically the IBM Q machines. And so essentially what we do is we're running Simon's algorithm on IBM, and we're trying to make sure how often we get back the correct results. And because when you run stuff on a quantum machine, you're going to get, like a real quantum machine, you're going to get every possibility within, and then you're going to get counts of how many times that occurred. And it should be a pretty high probability that you get what you expect back. And then Simon's also uses a 2-to-1 function. And in cryptography, there's a lot of 2-to-1 functions that are heavily used there. So I haven't really explored that idea yet, but if any of you are interested in that, obviously it might be worth looking into. I want to do that, but unfortunately time is something I lack a lot of these days, but maybe someday. So an example quantum circuit, this was actually generated from Qiskit. For whatever reason, it's putting certain unitary, and U2 means unitary, I believe, here in U3. I don't know exactly why it didn't put like my Hadamard gate specifically, but you kind of see where we have C naughts, and this kind of goes into what the algorithm generates. And then at the end here, we have these measurement gates at the very end here. So here's some of the results. I won't go too deeply into these. This just kind of shows there's so many backend. You can sign up for a free account through, I think it's quantumcomputing.ibm.com. I don't remember the specific URL, but it's free. You are limited on the amount of, they do like a credit system where each job takes so many credits, but you get them back after it's completed. And so these are just some rough results of the backends I had access to. Most of them were 5-qubit backends, which really isn't a lot to do much other than like a 2-bit string, because you got to remember you have to use bits for control and bits for data. So that limits you to 4 qubits right there. So let's see. And then there is a 14-qubit machine in IBM Q. For whatever reason, it's called 16 Melbourne, which made me think 16 qubits, but regardless, it is a 14-qubit machine, and I can do up to about 7-bit strings ran on it. And one thing I wanted to point out and I may cover this again later, there's 1024, IBM calls them shots, which basically means how many times the circuit is ran on the quantum machine, so you can get a random sampling. And you can actually adjust that depending on the circuit, and there's other parameters that may limit you, but I've done it up to like 2048 and 4096. But that's essentially, you send it, you get in a queue, send it to the IBM Q machine, and it just runs it that many times, and then you get your results back. Oh, cool, I can use my mouse. Sorry, I just discovered I can use my mouse to do the slides, but So here's I just decided to show you the black box piece of Simon's for a certain input, and I think the input string was 1-0. And the reason being is the other code is kind of pretty messy and long, and I just wanted to keep it to one slide. But it's kind of similar setup that you saw before, the Oracle here. This is what we had to kind of come up with on our, I don't want to say necessarily all on our own. There was actually an old Juniper notebook floating around that Ajinkia and I found. And so we based it heavily on this, but we had to do a lot of modifications to it because API changes and some other things that we didn't necessarily agree with the way they implemented it. So, you know, the Oracle essentially starts out that, you know, we go through here, we enumerate, and then we apply C naughts. We go through, then we get our list of random permutations, and we go through the permutations, and then we swap. We do a swap gate, and then we actually mark the swap gate, and then at the very end of the Oracle, we actually just randomly flip a qubit. Is all we're doing there, and then we have our barrier here that ends the black box function. And some sample output that I took just from the IBM QX2 backend, we have 1024 runs. Here's our period string. I think, yeah, this was correct. This is the correct string. It has a, actually, no, I'm sorry. It was 1-0. Was it? No, it was 1-1. Oh, I'm sorry. No, what it is the, these are the results you're getting, but it's taken from, I actually, in the research piece, I should have included this, that I have a function that goes through and verifies and basically does the inner product of everything to make sure this comes out correctly. So this is kind of, IBM doesn't necessarily do it in this way. They give you just kind of an object that you return with counts. I kind of made it a little bit prettier because I do a lot of stuff on the command line. I do use Juniper notebooks here and there, but it just really depends what I'm doing. And there's something I think, oh, that's one thing I wanted to mention too. And I'll talk about this in, I think, Grover's piece. But you have S equals S. You're basically reversing the list here, the string. And the reason being is the literature has the most significant, the endianness between a certain way, which I think is the left most significant, the least significant bit on the left and the most significant bit on the right, but IBM does it backwards. So to actually make it look more feasible to the literature and everything else that I've actually learned, it's easier just to do this. And otherwise you'll get gates going in, like going straight up when you're used to them going down. It's just kind of a make your life easier type of thing. But I wanted to point that out because that's something that's interesting that IBM does. So now I want to get into a little bit with Grover's algorithm, which is I have a lot more detailed research on because this is a part of my thesis. And Grover search is one of the first, it may even be the first quantum searching algorithms by Love K. Grover. And it was actually a huge inspiration for Shor's factoring algorithm. And it's been since improved vastly over the years, both Shor's and Grover's algorithm. And the big thing about Grover's is it's only efficient if it's unsorted and unstructured data. So if you give it sorted data and structured data, it's not going to do as well. And it makes heavy use and reference of what's known as the block sphere. And I'm going to talk a little bit about that. And this kind of goes back to the geometrical representation I mentioned earlier, that this really helps, at least it helps me to kind of visualize and think what a qubit actually is. And the block sphere, it's a geometrical representation of a two-level quantum mechanical system. When thinking about quantum computing, it's useful to visualize the block sphere as a model because you're dealing with you're not dealing with on and off constantly. I mean, you are, but you're dealing with rotations along the block sphere. If you think about that as like this big sphere, however you want to do it, it actually kind of helps, like, it's okay, this is intuitive. And this actually modeled off of different particles from that, say, like an electron or a photon, they have different spins. You can spin up, you can spin down, there's rotations, 45-degree rotation, 90-degree rotation, and so forth. And these actually map to, some of them, the X, Y, and Z gates, the poly gates. So you have your naught, you have your control Y, your Z, which is the phase. And then this is actually a drawing that this is actually in a lot of the textbooks and the literature of the actual block sphere. And it's, as you can see, once you kind of read a little bit more into it and what it's trying to do, it really kind of helps. You can see, okay, there's this physical thing here. I can measure angles based on that. I can rotate things. And I'll kind of get into why that's really important for Grover's here in just a second. And so Grover's uses what's known as amplitude amplification, which was initially created by I believe it's Giles Broussard in '97. And then later that year, Grover followed up, and I think they worked together on an advanced amplitude application. And really, this is to be fair, amplitude application is more or less a generalization of Grover's algorithm. And the fundamental idea is to increase or amplify the probabilities of the desired results. And this is accomplished by using a sequence of reflections, which again, kind of that's the whole quantum physics coming through. You have amplification of waves and so forth. And so what happens is the amplitude amplification causes the reflections to be rotated closer to the desired quantum state along the Bloch sphere. We have a target state we actually mark as sine squared theta, and the algorithm is actually repeated in times. And the probability of getting the correct state is sine squared 2n plus 1 theta. And so to put it more simply, we have a target state on the sphere. We keep rotating it until we find the correct result. And each rotation hopefully brings us a little bit closer to the desired result. And then this gets us into what's known as phase amplification. With phase amplification, we do a variety of operations to change the overall phase of the amplitude. But before my next sentence, I was going to say is going back to kind of wave mechanics. And then I know with quantum annealing, you guys have dealt with energies and so forth. That's kind of what we're doing. We have vectors of amplitudes, and then we're dealing with phases of these waves. So that's kind of where this is coming into play. So, and it gets a little interesting when you take it to the computing aspect, but I'll explain how it's applied here shortly. But before we get to that, say we have a lookup table. We want to search for our target value. Typically, you want to get a known key for this value, kind of like a hash table, which is really a cornerstone of my research, is that we have a key, we get our value, no problem, simple, quick lookup. But with Grover's, we kind of have to flip this upside down where we don't necessarily know the key, but we know the value we're looking for. And it may seem a little odd, but I'll try to explain some of my research, which kind of brings that into some use. And with phase amplification, for practical purposes, what it actually does, it does a phase flip. So when it comes down to the computational side, we're actually changing a positive to a negative or a negative to a positive. So for example, we want the value at row 1, column 3, which is EF. We do a phase flip, and now it's negative EF. And then going more into entanglement, Grover's makes very heavy use of quantum entanglement. So the way it works is we have a lookup table. This is loaded into a quantum machine, and Grover's algorithm will entangle all the permutations of a potential key and value pairs. And then the next piece, once that's entangled, the next piece is to do phase amplification by placing a tag value, so to speak, that equals our search value. And then kind of going back to wave mechanics a little bit there, which ties into the Fourier transform, there's a quantum variant called the quantum Fourier transform, which is the quantum variant of it. So there's a lot more. It talks about the quantum mechanics, and there's some different rules and so forth. And from a circuit level, you see a poly Z or just a Z gate or a control Z gate, which represents a phase flip. Now there's other variants, or you could do your own unitary version, which is kind of what we're doing in some of the research, but in my thesis, and you'll see, I'll explain that here. And then some of the performance and asymptotics. Now it's theoretically on an actual quantum hardware that has enough qubits, it should take big O of square root of n number of lookups on real quantum hardware. With simulators, this is a little bit of a caveat because the way that in fact, all simulators are implemented, specifically with Grover's, the way it's designed and how it runs, you have to visit every permutation with each iteration. So if you have 10,000 permutation and you have, say, whatever it is, like maybe 20 iterations, that's a lot. And so unfortunately, doing a direct comparison between simulating isn't really that feasible. However, in recent research, there is some research called the Schmidt decomposition, which is actually what's being used by the 49 qubit people and Google and so forth, which essentially is at a very high level. You're doing a type of decomposition of it, so where you can represent a state that you're looking for and a system with a lot less information. So if you can do things, which a lot of the algorithms now are basing off of Schmidt decomposition. And I'm not an expert on that. That's one of the things I have to brush up on and read more into, but this is pretty new, relatively new research. So I just haven't had a chance to go too deeply in it. And then comparing it to classical, a linear search based on the value, on worst case, we'd say big O of n number of lookups, because we have to basically look through the whole table. And then there's one thing we could do is, if this is provided, say we have a single linked list where there's just one going to the other, we could reverse this. So we actually have the value act as the key, and the key being the value, but we still have to go through the list, put it in a new data structure, and then look it up. So we don't really save anything there. And so getting to some of the practical uses of this is, for my master's thesis, and hopefully another paper submitted to the same IEEE conference, but we'll see how it goes, using this concept called n-grams, which are actually very useful in malware analysis and a lot of other fields. N-grams they make actual heavy use in NLP, neuro-linguistic programming, or natural language processing, excuse me, that's something else. Machine learning and so forth. And also like DNA sequencing, human genome sequencing, and so forth. So they're essentially just a string of characters that represent something to build features out of. So the idea here for the research is, we have some generated hash table from a malicious corpus, and we needed to get the actual hash of the byte string. So we know some byte string has some malicious properties, and we want to get the actual hash of it, because that could be useful information to a malware analysis for comparison or any other reason. A common thing is, if it's one or two hashes, they'll just go and rehash it through whatever algorithm they get. That's fine. But if you have a whole list of things, the asymptotics, you have M for the actual amount of characters you're trying to hash, then you have N for everything in the list. So this may look a little frightening, but this is actually some Grover circuits I came up with that they're not overly simplistic, but this kind of goes into the quantum simulation piece where I implemented on. Essentially what I want to show here is, like, you'll have, in a lot of literature, you'll see like /n, and that just means apply these gates to these n qubits. In this case, I did key and value to make it simple, and k and v. So for however many qubits represent our key, however many qubits represent our value. So we're applying a Hadamard, we go to our oracle, and then here in the index SBC, this is more of a classical implementation piece we're doing on the quantum simulator. And then we actually go through, this is our phase amplification piece where we're doing X Hadamard. And then this is where we're doing a zero phase flip, which is a unitary type of Z. And then we apply our Hadamard gates again. And then we essentially do another classical accumulator add, and then we do some measuring here. Though I think with Grover's, you can measure on one or the other and it doesn't matter too much. I got to double check on that. But the Oracle circuit, this will be kind of interesting as well, because you'll hear the terms uncompute and recompute. So essentially what this does is, we have a key and value. This is very similar to an assembly instruction of decrement. We decrement, we uncompute, we tag it with our zero phase flip, then we increment back to where we started. So in that, that simulator is actually called Crack, and it's actually by my friend, and he's been a good mentor of mine, called Dan Strano. And it's actually a C++, and I have some links to it in the slides. But so for Grover's, there's a couple examples out there, but I chose one with Qiskit because that's kind of what we've been using. And I know D-Wave makes heavy use of Python, so it's a little bit easier to transition to. And so the problem starts, we have these states, we tag these two input states of 110 and 101. And I'm using that term loosely, and I mean qubit 10 and so forth. But as mentioned before, the quantum endianness, so to speak, the most significant bit is on the left, and then it goes to the right. So in the actual, if you're looking at the actual code, 2 would be the bit on the left, 0 would be on the right, and 1 being in the middle, and so forth. And then this code was actually taken from another example from the textbook, but it looked like I couldn't really tell if there was an issue with the amplification gates or what they were expecting, or even their tag values. But regardless, based on what they provided and what their tag values is, I was able to modify this to actually make it work with the correct probability to get stuff back. So, and then with simulations, you know that you're going to get the values you're looking for with, it should be roughly equal probabilities, give or take. Depending, actually, you know what, that actually depends. So I don't want to paint myself into a hole there. And here's some of the results here. And yeah, I guess they're roughly equal, give or take. So, I mean, not exact equal, but pretty close. So we have 8 different possibilities, 2 correct answers. And I ran this on a Qiskit built-in simulator. There might be a little bit of error in the way this was output. This might be from the old code. I have to double check on that. But we have the correct state, 277 results, which has the most. And then we have 258, which is the next, which is the other. If we I think I can go back, we can see those were 110 and 101. Those were actually our tag states. That's when it's actually ran. But I'll go over the code pretty quickly here, and you guys can obviously, it'll be on GitHub also. You guys can check it out on your own. So import stuff, load it in our account. We have Grover circuit, we build that. We have a phase oracle here where this is actually where we're tagging the actual value. Then we have our phase amplification, which we're applying Hadamard, we're applying X, and then we're doing a Hadamard again, an X, Hadamard on the most significant bit, X on the middle one, and then a control Z or on, yeah, so from the least significant to the most significant, and then we do a Hadamard again on the most significant, and then we apply Hadamards to everything again, barrier it off, apply our phase or query our oracle, and then we do our phase amplification. And so then we kind of go through. I left some of the state vector stuff in because it's actually really useful to, and the reason I bring this up, I didn't actually have the down, I just had that up to the measurement piece. State vectors are very useful in that you can get sometimes approximations of the exact same results, but you could be getting different, you could be getting the same numerical results based on approximation, but you may not have all the actual state may be completely different. So using and analyzing the state vector, that's actually a very good debugging way to get in to say, okay, maybe they yield the results I expect numerically, but when I do other quantum experiments, they give completely weird stuff I don't expect. So comparing the state vectors is useful. Let's see. Oh, I think that's, trying to think if there's anything else I wanted to talk. Oh, the one thing I didn't want to mention. So on a quantum simulator, this is true of Simons as well. You're essentially going to get the correct answers because there's absolutely no noise in a simulator. Now, Qiskit actually has a noise simulation, which I've not had a chance to study too much of yet, but the where you can essentially emulate noise, and you can actually download the noise model as well as the bit mappings for that, and then basically use it in the simulator and change it how you want. And there's a whole bunch of levers and knobs and parameters to play around with. But on the real quantum hardware, you're going to get every possibility because there's going to be usually some count of, say, what are some of the possibilities. So you have, in this case, say I had 8 possibilities, I'm going to get numbers for all 8 possibilities. But if it's done the way I expect it and what I want, the highest count should go to the higher probability, so to speak, should go to what my expected results are. So I'm trying to think if, okay, I think that's really all I have. I have some stuff a little bit at the end I'll post here, but I want to open this time up to some questions, or if Raman, you had anything else you wanted me to talk about, or?
Thank you so much, Nick. Can you hear me?
Yeah, I hear you.
Okay, and I really enjoyed your presentation, and I guess for most of students now they can see that quantum computing is not just about D-wave quantum annihilers. There are many other areas that if somebody is interested in quantum computing, they need to explore. And these 3 algorithms, Deutsch, Joza, I still have a hard time with pronouncing their names, and the Simons algorithm as well as Grover's algorithm, they are, from my personal perspective, as Nick said, they are somehow the primary or basic quantum algorithms. And I do think that in Quantum Zoo, which is the repository for quantum algorithms, more than 200 new algorithms have been proposed based on Grover's algorithm. Mm-hmm. I have seen that people are using Grover's algorithm for solving Boolean satisfiability problems, constraint satisfaction problems, optimization problems, and also the advanced versions of or modified versions of amplitude amplification has demonstrated to outperform the best known classical computers in solving, for example, SAT. One point for Grover's algorithm is that it only can provide quadratic speed up. So when we want to use, for example, a quantum computer to solve a SAT, let's say a Boolean formula with n variables will have 2 to the power of n different possibilities. If you apply Grover's algorithm to satisfy a Boolean formula, it will quadratically reduce the search space, but the best classical algorithm performs better than that. However, there are extended versions of Grover's algorithm and amplitude amplification that can do better job compared to best known classical algorithms. So these algorithms are somehow fundamentals in gate model quantum computing. And if someone wants to explore quantum information processing, I think these are essential and fundamental.
Yeah, absolutely. They and you're absolutely right about Grover's, because I'll search on the archive, and when I wanted, I actually had the most difficult time finding Grover's original paper, because there were so many papers out there that were modifications of Grover's or using them for other applications, and I'm like, I want his original work. I don't want all this other stuff right now. And that was actually, that was a challenge. I mean, I'm not even joking. That was really hard. And I eventually found it, and then Simon's is kind of the same way. There's people using it for other interesting pieces. It's like, I want the original work so I can cite it. And I myself, when I go back to the foundations of where it came from, I get the most out of it based on somebody else's work of it, so to speak, because I can kind of get in their head of what they were thinking. But yeah, it's crazy just how much it's been advanced. And then there actually has been ways with Schmidt decomposition that Grover's modified to take advantage of that. But I'm talking about obviously this classical implementation of Grover's.
So let's see if students have any question. If you have any question,
Yeah, feel free if anybody has a
I
question.
think somebody asked a question in the chat or QA session.
Yeah, I do see that from Swapnil.
Yes.
Yeah, on my chat window up. So
You can, if you have a question, you also can unmute your system and ask it. That's
Okay,
up to
all right.
you.
Yeah. So I'll go ahead with my question. So you mentioned about the decomposition of the input. So I'm trying to understand that. Are you referring to that principal component analysis, or like tensor decomposition, those terms in machine learning domain?
I'll say at a high level to a point, and that's kind of when I was explaining Schmidt decomposition, is it's kind of along the same lines. If you know what SVD of a matrix is, obviously, if you're talking about machine learning and tensors, I would hope you do, then yeah, it's kind of along at a high level the same lines, where you're getting these pieces of information about the state of a system, and you can represent and do things to that, and then those are key pieces that you can do things in a more optimal way with just those to a system, because those are actually derived from the eigenvalues and the eigen pieces of it. So yeah, it's along those lines of thinking, even though if it's not exactly the same. But with tensor decomposition as well, that's actually another thing I'm looking at with Dr. Nicholas, is tensor decomposition for to see what malware classifiers might look like, and then look at possibly how a quantum algorithm with tensor decomposition would. But machine learning is actually one of the big drivers for quantum computing, also that research in AI. And there's, I think Dr. Dorban here got a Boltzmann or a partial Boltzmann machine running on the D-Wave. And then IBM and other people they've been able to implement quantum versions of machine learning. And that's really where a lot of research is being funded too. So the idea is that, especially if you're getting into neural networks, because quantum computing kind of model is almost a perfect model to run a neural network on, because neural networks, essentially you get things, you just let them go and collide into each other to form things. And then quantum computing kind of we can take full advantage of that. And there's definitely a lot of work being done there.
Okay. And addition to that, you also mentioned that if suppose we have let's say 50-bit string, and to try out all the combination, it takes so much time, and it's computationally expensive. But my point is that isn't that the advantage of quantum computer, that we can do simultaneous computation of all these combinations?
And that's correct. Yeah. So that's where the entanglement comes in. So you have pieces, particles, data, whatever. You entangle them together. You apply your gate operations on the qubits once they're entangled. Then, yeah, or even if you affect one qubit or the other, you're applying it to everything that's entangled. And then you try to uncompute it, so to speak, to a completed state, so to speak, where after everything's been applied, if you could potentially unentangle them, so to speak, that's a whole other line of thinking. But that's the idea, yeah. So you're essentially doing mass parallelism, like true
Mhm.
parallelism, because if you look at distributed computing, and even though it's good in a lot of ways, especially with the supercomputers and whatnot, and you still have like coordinators and threads, so forth. But you're still doing things in a you're doing it very, very fast, but you're still doing it in a very linear fashion, one after another. You're doing it very, very fast, and it may be on a couple of machines doing it at roughly the same time. There's still time slices there, and there's still a little bit of a delay, and that's kind of, you might be splitting hairs a little bit at that point, so to speak. But yeah, that's a huge benefit there too, is that once you entangle stuff, you apply operations, whatever you want to do, and it applies to everything at the exact same time. And that's where it takes advantage of the quantum mechanical phenomenon.
Um, uh, Also, I have one more question. Can I ask?
Yeah, I don't mind.
Yeah. So you also mentioned about something about hash map, and how you were able to do reverse mapping and figure out the output. So did you do this computation, or the calculation on classic computer or quantum computer itself?
Are you
Like,
talking about my thesis specifically?
yeah, that hash map thing you
So
mentioned.
what I had to do there, and that actually has to do with a lot of limitations of one, usually what's currently available with quantum computing, like publicly. So I couldn't really do a whole lot there. I could, but it would be pretty difficult with 5 qubits. It's not a lot. Even the 14 qubit one would be kind of difficult. But I did it
Mhm.
using a simulator called Crack, QRACK, and I'll actually have some links here shortly
Okay,
um,
okay.
about that. And then it'll be, and actually, let me go to that now because I can.
I would like to comment on.
Yeah, so here's actually the links to my GitHub and
All right.
Simon's and the masters that has a lot of this code on there. You can look.
Thank you. And as as uh, as previous sessions, we will share the videos, and Nick agreed to share the video. So if you need, you can scan the QR code. Regarding
Mhm.
quantum computing, I would like to quote an example from Dr. Tayor, who is a faculty at Carnegie Mellon University. I met him in D-Wave annual meeting last fall, and he had a nice example. Let's say you spend some $1 million to buy a race car. If you take it to downtown Baltimore and you compare it with like a $5,000 machine, you wouldn't see too much, difference. But it doesn't mean that like some $1 million car is as good as a 5K machine or car. The point is, if you want to have a fair or right comparison, you need to have the proper environment, like the road that you can take advantage of your some $1 million car. Also, you need a good driver. Problems could be assumed as the road or environment, and scientists could be those drivers. If we want to show that quantum computing can uh, outperform classical computing, even supercomputers, then we need to find good problems, proper problems, and then have good, proper scientists to work on. Quantum computing is good for certain types of problems. And when we want to think about applying a quantum computing for a specific type of problem, I think it is a must to think that, are we going in the right direction? Is this a road that we want to race with our some $1 million car?
Yeah, makes sense.
Any other question? We still have
I
a
had a
few
question.
minutes. Sure.
So I'm diverging back to the Grover's algorithm a little bit. Uh, can you like briefly explain how to actually identify what the Oracle function is? Like how do you tag specific bits or specific states that you want the Oracle function to output?
Code piece, or are you talking like here? Is this what you're talking about?
So here in your phase Oracle, you've just put control Z
Correct. So
gates
I'm
on
doing
two
control Z.
tags.
Correct. That's just a function to do control Z here. And remember, this is something that
Mhm.
actually tripped me up too. Is when you first go down to here, the very first thing you do is you're putting a Hadamard gate on everything. And remember what a Hadamard gate does? It puts things into superposition. So you have a 1 and a 0 on that qubit. So one of the 1 in that superposition is going to trigger that control, and that's gonna do the control Z on the bit.
Okay.
Does that make sense? That's kind of something that tripped me up too for a long time, actually, is that
Yep.
you look at that and like, well, this is targeted. Why is this working? Like, okay, you have a Hadamard. That's you have 1 and 0.
This is the way it works in an anomaly.
Hello. Okay.
Yeah, sorry, I don't know. I think someone was trying to
Okay.
talk. Jumbled and weird sounds.
Yeah. Also, like another question about growers is like we implement phase like amplitude amplification after identifying the tags, right? So how do we know how much the phase should be shifted to find our correct tag or like amplify the probability of the tags that we want? Like what's the operating procedure here?
For the control Z,
Uh,
so I'm trying to understand what you've asked. That what?
so so we want to amplify the probabilities of our tags, right?
Yes.
But like how do we actually achieve it? Like how do we change the I understood that we switch the flips of the tag that we want.
Right.
Just that increases the probability, or do we have to do something else?
So the phase, like the phase oracle, doesn't really do anything with the probability. That's just doing the tagging. That's actually the probability pieces. That's actually coming in with the phase amplification pieces. So if you sorry if I'm jumping around here real quick, but if we kind of go back to the circuit model here,
Mm-hmm.
we have our oracle here. The oracle is relatively simple. For all our qubits, we essentially roll the block sphere, so to speak. We tag it with our values, then we basically roll it back to its starting position, and then we trigger that, and then we go on, and then mathematically it works out. But we essentially we flip, then we do another Hadamard, which takes it out of superposition, and then once we're out of superposition, that we have our value, and then we do a unitary Z, which that's actually once we've essentially rotated to that point, we actually flip the phase again, and then we put it out here in superposition again, and then we actually do a measurement, which actually will collapse it down. Well, collapse is the in quotes here. So the magic is
okay.
more in the control Z. If you're speaking about like the mathematics behind it, I'd have to get back to you on that, look up the specifics on that.
No, I read like about Grover's algorithm because my project for this course is based on that.
Okay.
So like they mentioned that there's something called Grover's iteration, and you like repeat the process. So are they mentioning that we are repeating the amplitude amplification process multiple times?
Thank you. That's exactly where, when I talked about the asymptotics, you have you're doing it. So that's the idea, is you basically, the way it works is the idea is you basically measure once, then repeat it. You just repeat this whole circuit so many times. And there's actually a mathematical thing that's proven for the amount of times, and I didn't include it here. I probably should have now, but it but correct. Essentially, it's the square root of whatever your input is, and that's how many times you're repeating it. So if you have a very large, or the number of qubits, I believe it is. Yeah, exactly. So you essentially you just have to keep applying Grovers over and over and over again, and then you eventually, within a certain probability of 100, hopefully 100% probability, get the result you're looking for. And that's actually what kind of comes to the rotations here. And that's what you're, so each application rotates it some and does phase flipping and calculates it, and then you apply it again. It does it a little bit more. You repeat it and you repeat it, so to speak. So you can kind of, yeah, you can exactly think of it like a loop. I think that's I don't know if I have it in the code like a loop. Yeah, well, so these pieces here, the Control Z isn't,
Okay.
but what we're doing Hadamard's and NOS, that's actually the piece we're going
Oh,
through.
okay.
Yeah, so yeah, you are applying it more than one occasion. That's correct. Thank you
All
for
right.
bringing that up. I was like, wait, I'm like, okay, yeah, you do have to do multiple iterations of it. But the idea is that we would have to do less iteration. If it's true quantum hardware, the idea is we would have to do less iterations than on a classical machine to do a value-based lookup, at least with the lookup table example. And there's other applications of it as well.
Mm-hmm. All right. Thank you.
Yeah.
Thank you. We can take one more question if there is any. One more question. Okay, last call. We are closing the deal. Okay, let's thank Nick. Everybody, we electronically or virtually thank you so much for your time. Again, based on the timing and your schedule, I really am surprised, and I do appreciate that you share your knowledge and experience with us. And I hope that it can help everybody, including myself, to explore gate model quantum computing more. And before the class, I mentioned that there's a big announcement that has been scheduled for supercomputing conference, but we may see a 100 qubit system sometime very soon, either this summer or fall, publicly either available or announced. And there's a term called NISQ, noisy intermediate scale quantum devices. And in that regime, we may see systems with 1,000 or a few thousand qubits in near term. So I do think that there are a limited number of technologies that will play a crucial role in next decades. And quantum computing is definitely one of them, including AI and biotechnology. But I do think that we'll see and hear more and more about quantum computing. And these three algorithms are somehow fundamentals of gate model quantum information processing. Thank you so much, Nick. And I do appreciate your time. I hope that we didn't take too much of your time. And
I'm flattered and honored you asked me, and I wanted to kind of give a quick special thanks to Dr. Lamonaco, Dr. Nicholas, who's my advisor, Dr. Edward Rath, who's been helping me on I'm actually using some of his existing research in my thesis for the malware engram stuff. Ajinkya Borle, Dan Serrano, who actually wrote Crack, which is the C++ OpenCL quantum simulator that's really, really efficient, and he's making progress to it constantly. And he's actually trying to compete with some of the Google, trying to do some of the quantum supremacy stuff on it, which is actually really cool. And I especially want to thank Raman for asking me for coming and speaking today. And I also want to congratulate him on his defense last Friday. It was, I learned a lot about quantum annealing there too, and the Boolean satisfiability and your modifications to it.